The last of the main themes that we'll be covering in the chemistry part of Biology 1. This includes acids, bases, and buffers, which are all extremely important for how biological systems work. We're going to be looking at the pH scale, which you might be familiar with already. It goes from a 0 up through a 1 up to 14. 7 is neutral, and what you need to actually understand is that this is basically it's a logarithmic scale, which means the concentration of acid increases as you go with these smaller numbers, so that this is very acidic, whereas the concentration of acid and the decreases and the concentration of base increases as you go up to 14. So 14 has a very, very low concentration of hydrogen ions, which is what an acid actually is, whereas a 0 has a very high concentration. Beyond that, you don't need to know a whole lot until you get to chemistry, but know that distilled water, plain old water, is 7. Anything above 7 is going to be a base. Anything below 7 is going to be an acid. This comes about because water can actually break into hydrogen ion, which is where the hydrogen atom gives away its electron, lets the oxygen hold on to it. That means oxygen and hydrogen here, which is called the hydroxide, which remains, that has an extra electron and a negative charge. This has the electron missing. It's basically just a proton, and it has a positive charge. This is something that water does at a very low rate, but it is something that water does. To look at this another way, if you had two water molecules, one of the hydrogens pops off of water because this hydrogen ends up being so attracted to the oxygen, it pops off of this water and joins onto this one. So this is a water molecule with an extra hydrogen ion on it, which is basically another way of representing an acid. Acids are either H+, if you choose to look at it without the other water molecule, or it's an H3O+, which is one extra hydrogen ion on a water molecule. And then one of these electrons stays behind, and this becomes your hydroxide. So you're splitting water, you get a hydrogen ion, which is a characteristic of an acid, and you get a hydroxide, which is a characteristic of a base. In neutral water, pH of 0, in this kind of situation, what we call hydronium and hydroxide are equal in balance because it was formed from a water splitting apart. But if you're ever in a situation where you have extra hydrogen ions, you have an acidic solution, an acid. Aqueous, that word means that it is dissolved in water. Agua, water, solution is aqueous solution. So if you have extra hydrogen ions floating around, which are really the same thing as what we call a hydronium, which is a water with an extra hydrogen ion on it, then you have an acid. If you have extra hydroxides floating around, which we call this the OH hydroxide, then you're going to have a base when it's dissolved in water. And acids and bases will neutralize each other. I'm hoping we'll have at least one experiment where you get to see that. These are the names of some common acids and bases. Now remember what I said. Acids will increase your hydrogen ion concentration. Look what the acids are made of. Hydrogen, hydrogen, hydrogen. These are the hydrogens that will come off into the acid. These will what we call dissociate. The hydrogen will pop off, become a hydrogen ion, and you have a chloride ion. Or you have hydrogen coming off here and you have phosphate. You have hydrogen and nitrate, hydrogen and sulfate. This is acetic acid. It's actually this hydrogen that pops off and becomes an acid. Carbonic acid, these hydrogens can pop off. So that's what makes an acid. These OHs pop off. These H's pop off and form your acid. Now, I was looking over here. The bases are where the OH pops off. So here's where I can increase my amount of hydroxide because I have sodium hydroxide. Sodium has a plus charge. That dissolves. Hydroxide has a minus charge. This is an ionic compound. When I have extra hydroxide in my solution, I have a base. That's what makes it basic. You'll get to work with sodium hydroxide in a lab. That is a base. One other interesting compound is ammonia. Now, ammonia, when it dissolves in water, ammonia has the ability to pull one hydrogen off of water. Hydrogen will jump from here, go on to nitrogen, leaving behind an OH. So even though ammonia doesn't have an OH like most of these bases do, because remember the definition of a base is extra hydroxide, these all easily put the hydroxide in. This one does it by letting a hydrogen pop off onto this ammonia, making it ammonium, and you have a hydroxide left over because hydrogen leaves that extra electron behind. Now we use the pH scale in order to determine whether something is acidic or basic. Alkaline is the same definition as a base. Bases are alkalines, alkalines are bases, acids are acids. What we're actually measuring is the concentration of hydrogen ions. So the lower the number, even though it's a little strange to see, the lower the number actually means a higher concentration of hydrogen ions, which means if I have a 0 or a 1, that's very concentrated. Very concentrated hydrochloric acid, one of the strongest acids, can be a 0, whereas weaker acids, tomato juice, coffee, those are fairly weak acids. They have a much lower concentration of hydrogen ions. At the same time, if I go above a 7, I have really small concentrations of hydrogen ions. I have much higher concentrations of hydroxide ions. And the other thing that I need to know is, because this is a logarithmic scale, which you probably won't have much with logs until pre-calculus or algebra 2, but what happens here is that if I go from a 6 to a 5, that's actually a jump by tenfold. So coffee has 10 times more hydrogen ions than urine, which is P. And then coffee has 100 times less hydrogen ions than orange juice, or orange juice has 100 times more hydrogen ions than black coffee. Lemon juice would have 1,000 times more than black coffee. And gastric acid, that's your stomach acid, that would have a 10,000, because here we go, 10, 100, 1,000, 10,000 concentration in the increase in concentration for hydrogen ions. Some of the things you might see in daily life, our blood has a pH of 7.4. It's slightly basic. That's a good thing. If it goes outside of that range, we're in big trouble. Even if you dip out of this tenths to 7.3 or 7.5, we're in big trouble. Milk is slightly acidic, so is saliva. Battery acid, which is sulfuric acid, very low pH, a 0 or a 1. Lemon juice is a 2. Sodas are in the 3 range. This is why soda can be damaging to your teeth. The basic things, baking soda, ocean water, although ocean water, as we will see, ocean water is becoming more acidic. The pH of the oceans is dropping, which is kind of a scary thing that's going on. Ammonia, we talked about already. Bleaches, very high pH, and drain cleaner is usually sodium hydroxide or potassium hydroxide. Very, very strong bases. This is kind of a review, but what you need to know is acids release hydrogen ions in solutions. Now, those hydrogen ions are represented as H+, or if that jumps onto a water molecule, instead of being H2O, it would be H3O with a positive charge. That's your hydronium. Weak acids generally have sour tastes to them, so that's like lemon juice. Soda, slightly sour. Orange juice has a little bit of sourness to it. Those are your weak acids. Strong acids will go eat through most any natural living tissue. So battery acid will eat through your mouth if you tried to taste it. There have unfortunately been acid attacks where people get their skin damaged from strong acids like battery acid. So don't go around the strong acids. Hydrochloric acid, another one, will work with it. Don't get it on your skin. Don't get it in your eyes. Vitamin C is an acid. One of these hydrogens actually comes off. Citric acid, another very weak organic acid. This phosphoric acid is what's in soda a lot of the time, gives it that kind of a sourness, which is balanced by the sugar, and that's what gives soda its taste. So just so you're aware, these are some examples of acids. We saw some other ones before, the very strong ones, sulfuric acid, nitric acid, very strong acids, hydrochloric acid, very strong, phosphoric acid, not very strong, acetic acid, that's vinegar, not very strong, carbonic acid, not very strong either. This is what happens, just so you get an idea. I have a compound, hydrogen chloride. When hydrogen chloride goes into water, it does what we call dissociate. The hydrogen ion comes off, leaves behind its electron with the chlorine, which is why the chloride has a -1 charge. Hydrochloric acid, very strong acid. It will dissociate completely, leaving a whole bunch of these hydrogen ions, which means the pH is going to be very, very low because a lot of hydrogen ions are concentrated in that solution. pH is extremely important for living systems. The reason why is because we have proteins. This particular protein is an enzyme. Enzymes do specific chemical functions within the body. We have certain enzymes in our stomach, in our large intestine, in our cells. They all have to operate at a very specific pH. If they don't get to work in that specific pH, the protons, the hydrogen ions, which really, if you think a hydrogen atom is a proton and an electron. You take away the electron, you have a proton. If I take these proteins, which are all nice and normally operating at a certain pH, and I flood it with a lot of these positive charges, well, those positive charges cause the molecule to completely denature, which means it twists completely out of shape, and it's no longer functional. This is what happens. The same thing would happen if you cooked an egg. You have these nicely ordered proteins in the egg white. You cook it, they get all tangled up. You can actually basically cook an egg with a very concentrated acid. You get the same exact thing, although I would not recommend eating that egg that you cooked with the acid because it will still have the acid in it. Now, weak acids do not dissociate very much. So this is acetic acid, this is vinegar, does not dissociate very much. You see a lot of these molecules stay together, which means that the pH is not very low because while there are some hydrogen ions, there aren't a tremendous amount of them. And remember with pH, the lower the number means the higher the acidity or the higher the hydrogen ion concentration. This is acetic acid. Bases, as we said before, they release hydroxide. A lot of these have the name hydroxide in them. So we saw sodium hydroxide, potassium hydroxide, barium hydroxide, calcium hydroxide. They all release these OHs into the solution. They are called alkaline substances. This says hydroxyl. I prefer hydroxide. I didn't go through all of the terminology yet. Some bases will have a bitter taste. Some bases will turn your skin into soap. So if you get sodium hydroxide onto your skin, it actually interacts with the fatty molecules in your fingers and will start to turn them into soap, which means it's eating through your skin at the same time. So stay away from the strong bases. Bleach being one of those bases, sodium hydroxide drain cleaner being another. So this is a very dangerous one. You don't want to get it on your skin or in your eyes. This one is not quite as dangerous. It helps to neutralize acid in your stomach. You can drink small amounts of it, although you don't want to drink large amounts of it because the magnesium can actually stop your heart if you're not careful. So take it only within the recommended doses. Bases, again, if we're working in this area, nothing really to worry about. But where we get up here, we got some danger. And that's stuff that will generally turn your skin into soap. It's very corrosive. It'll eat through your skin, it'll eat through your eyes, eat through any of your body tissues. Bleach, same thing. If you tasted it in your mouth, it would start to eat through your mouth. Sodium hydroxide, even more so. So let's stay away from the strong bases. What organisms need to do is maintain a balance. Most life operates within this range, but we do have certain cases like our digestion in our stomach. We need a very low pH for that, but we can't let what's in our stomach get into our blood because that's going to completely mess up our blood biology, the proteins in our blood. So a lot of what our body does is maintaining homeostasis regardless of what happens on the outside. Now, if my stomach acid at a pH of 2 ended up getting into my blood at a pH of 7.4, it's going to completely mess up my proteins in my blood, and I'm going to die from that. That's why we want to avoid, injury to stomach, for example, where something like that could happen. And beyond that, our body is constantly working to do things within homeostasis to maintain our stomach pH at a 2.3 or between a 2 and a 3, and our blood at a 7.4. This is something our body does to maintain a stable environment inside of our body, which is what homeostasis means. And we need these different conditions because of certain things that happen in our body for digestion or for transporting through our body. Proteins need to be a certain shape. Enzymes need to break things down. We just have to have these different pHs in order to operate effectively. One way our body does this is what with these chemicals we call buffers. Certain salts will either grab extra hydrogen ions or grab extra hydroxide ions, neutralize them. It keeps things from becoming too acidic or too alkaline. It helps to maintain them at a certain level. We'll talk a little bit more in depth about buffers, but I just wanted you to be aware of that. So if you have too much acid in your stomach, you have acid stomach, you would take something like calcium carbonate, which would then break down the... I'm going to have to fix this. So calcium carbonate will help neutralize the acid in your stomach, which if you have pain from too much acid in your stomach, that's something that you would want. We'll talk more about buffers, but you have buffers in your blood. You have buffers in your intestine to maintain when all of that high acid stuff comes out of your stomach, goes into your small intestine, needs to be neutralized. Then you have buffers that maintain those specific pHs. One of those, I needed to get a better image here. Actually, I should just delete this whole slide. We'll talk a little bit more about that next time. And this I thought I had deleted. So I will make another independent video on buffers. Buffers are really the last thing you'll need to worry about before the test. So, thank you.